All right, gather around, children. We're going to learn about Gauss's law and Gaussian surfaces. So, all right, I should probably start it up here. So, technically speaking, we're going to be looking today at um, the divergence and curl of electric fields. So, if you remember from last time, or if you weren't here last time, that's fine. Um, Last time we kind of developed, what electrostatics is about, uh, in electrostatics, whenever you want to solve an electrostatics problem, generally speaking, you want to find the electric field of some charge distribution because you want to know the force it exerts on another test charge. And so last time we went through and we found out and we found this formula for calculating the electric field. Hang on. I want to use red. There we go. And we found this formula for calculating, in general, the electric field of some arbitrary charge distribution. So, this tells you that if you have some charge distribution rho, um, then the electric field generated by this charge distribution is this volume integral of rho over the distance between the charge distribution and where you're looking at squared. Um, yeah. So that's all fine and good, and that does hold for any charge distribution. However, as we kind of saw from last time as well, there are two issues with this method. One, rho of r is never really pretty in reality. Like you can talk about line charges and certain like sheets of charge, but like most of the time it's some amorphous blob, and it makes and it kind of like what ends up happening, even if you have symmetry like a cylinder or a sphere, or not a sphere, yeah, even a sphere, um it causes problem number two with this formalism, which is integrals suck to do. I don't know where Aleph stands on this, but actually calculating integrals is never fun. um the entire goal of physicists, or what physicists tend to want to do, is to avoid actually calculating as many integrals as possible. Hey Astral, how are you? So like physicists, we're lazy. We don't want to actually do any math. So we have this way to calculate the electric field, but it requires us to solve an annoying integral, which leads us to the question, is there any way we can make this easier on ourselves? And so, in order to answer this question, what we will do is first, we're going to look at a quantity called the electric flux. And so, I had the page and then I lost it. Hang on. Okay, yeah. So, we are going to look at a quantity called the electric flux. And we denote this quantity as phi sub e. And the electric flux is defined as, so if you haven't seen this before, three line equivalence means defined as. So this is true by definition. The electric flux is defined as the surface integral of your electric field over some surface. And so you'll notice phi, the neutrophil. Maybe you should ask him if he carries a net electric charge. Um, I don't know. So yeah, so you'll notice what. Yeah, so the thing that I want you to notice is Oh, I keep forgetting I have ads because I'm used to it telling me as a mod on Nep's channel. But yeah. Um, Phi. So yeah, so there's no circle on this integral, which means that this is not a closed surface integral. So S can be either open or a closed surface. Aw, thank you for the gift sub, Tyler. So yeah, so what does this flux actually tell you? Like, what does this represent? Um, Generally speaking, this tells you roughly how much E field flows. Hang on. All right. This tells you roughly how much E field you have flowing through your whatever surface you're caring about. And so the reason why, for those that aren't as calculus brained, which I totally understand, um, what it does is it takes E, how whatever component of your E field actually passes through a surface. Because remember, I think I mentioned it either two streams ago, but we can turn some area element into a vector by defining the area vector to be pointed perpendicular to the actual surface area. So this dot product tells you how much of the E field actually passes through a surface element, dA or ds. And then, like I said, the integral is a fancy addition symbol. So it adds up the tiny all the E fields that pass through um, your incremental surface area elements and adds it up over the whole surface that you care about. And so I have prepared this time some graphs to help better illustrate this. Um, so if we look at let's look at the this graph on the left first. So um, I don't know why the legend didn't work for this left graph when I made it. Um, Python, I love Python, but matplotlib for 3D plots can be a bit janky sometimes, and yeah, I just didn't want to fight with it anymore. But yeah, so if I zoom in, these blue arrows represent um, the electric field of some point charge that's centered at the origin. And so I'm gonna use red, right? So I have some point charge at the center of this region, and it creates these electric field lines pointing out of it. So, for instance, if I wanted to draw some arbitrary sphere around it, then the electric flux would be how much uh, of the E field that this charge creates passes through this sphere. And so the trivial answer in this case, because as you can see, all of the E field has to pass through the sphere at some point, is that this flux is going to be non-zero. Um, but this is not always the case. Um, Actually, before that, let me go over here because this might be easier to see if you imagine this as like a 2D slice of the point charge. Then, as you can see, all of these E field arrows have to pass through the surface at some point. And so keep in mind that that dot product also has a sign with it, right? So since you have all of the E field arrows pointing out of the surface, none of them cancel out on each other. But again, like I said, that is not always the case. For instance, if you take a dipole, so this is a model of a point dipole, right? which is essentially just you have a positive charge on the right, a negative charge on the left, and this represents the net electric field generated by these two charges. And if you'll notice, if I draw a sphere, and this is a sphere, the graph itself is just not scaled uh, 1-to-1, that the flux through this sphere actually becomes zero. And it might, you can kind of see it as you have the field lines. Oh, hang on. There we go. You have field lines here, right? And they're coming into the sphere, into the circle or sphere, whatever. Um, but at the same time, on this side, you have arrows going out of the sphere. Same here as well. And so if you actually calculate the flux integral, all of these contributions cancel each other out, and you're left with zero. And now you might notice a trend with these two situations. Up here, if you calculated the flux over this sphere, you'll notice that, like I said, this integral ends up being non-zero, and I'll do this integral in a second. And it's that, and that tracks with the net electric charge that you had inside that surface that you drew. Whereas down here, the net charge enclosed by this circle is actually zero, because the positive and negative cancel each other out. And that corresponds with the fact that our flux integral ends up being zero. So that begs the question, what does the flux integral actually have to do with the electric charge? Hang on, let me get to a blank one. So let's figure that out. Let's answer that question. So to motivate this idea, let's calculate, let's do the flux integral for that point charge. So if you remember from last time, the electric field of a point charge is Q over 4 pi epsilon naught r squared r hat. And I'm just going to say it's placed at the origin. So your r, your source vector is just the zero vector. That makes this easier. So I want to calculate the electric flux over a sphere. So you have Q over 4 pi epsilon naught 1 over r squared r hat dot ds. Yeah. All right. Sorry, I should, before I move on with this, is that tracking so far? I know Astral, this should make sense to you, but just in case. Cool. All right. So like I said, this surface area vector, the direction actually points perpendicular to the surface. And if you'll notice back up here, perpendicular to the surface is exactly just the radial direction, r hat. It's the same. So the surface area element and your E field are exactly parallel. So ds is, and because we have spherical symmetry in this problem in particular, I'm going to express this surface area element in spherical coordinates. So that ends up being r squared sine theta d theta d phi r hat. Where if you look at, I don't know if I can draw a sphere. if you imagine a sphere, this is your r hat direction. Theta is the polar angle. So if you think about latitude on Earth, polar angle theta represents how far away from the poles you are. Um, and then phi, or phi, as some people call it, represents your azimuthal angle, um, basically your longitude. So yeah, so if we plug this in, and so we want to integrate over the sphere, um, so that means that we want theta to run over this half circle, so that would be 0 to pi, and then you want your azimuthal angle phi to run over the whole circle, the whole longitude, so that becomes 0 to 2 pi of q over 4 pi epsilon naught 1 over r squared. R hat dot r hat is 1, so we're left with r squared sine theta d theta d phi. All right, so you'll notice something kind of easy. These r squareds cancel out, and so you're left with q over 4 pi epsilon naught integral 0 to 2 pi integral 0 to pi of sine theta d theta d phi. And I'm going to skip the actual math. This ends up equaling 4 pi. So the 4 pi cancels with this 4 pi, and you're left with q over epsilon naught. And you are left with a very interesting correlation. If you take the integral, the surface integral of some charge over some, like, around some charge distribution, you calculate the flux around some charge distribution, that flux is directly proportional to the amount of charge that was inside that surface you drew. And so this actually ends up holding true for all closed surfaces. Ignore that for now. I did not predict my space properly this time. So this time I'm going to use this circle to represent a closed surface. So the closed surface integral of E dot ds is equal to the amount of charge enclosed by your surface over epsilon naught. Bum ba bum. And this very powerful fact, because as you'll see in a bit, this actually exploits the symmetry of the problem, and you end up not having to do this integral a lot of the time. This fact is so powerful, we gave it a name. And we named it Gauss's law. Bum bum bum. Also, yeah, I forgot to point out, but Astral has graciously allowed me to have my ancestor sit in with me. Yeah, that's what I'm gonna call him. He's my ancestor, Carl Gauss, the original Gauss. So yeah, this is the integral form of Gauss's law. We also have a differential form as well. So we can convert this by using let's go down here. So we can convert between the two by exploiting one of Gauss's other theorems. So Gauss has another theorem in math, otherwise sometimes also called the divergence theorem. Um, the closed surface integral of a vector field ends up equaling um, the integral of the divergence of E. Yeah, Gauss was too powerful. I remember he proved the summation of like consecutive integers equals like n times n plus 1 over 2, I think. Um if I remember correctly, he proved that when he was like a teenager or something. But yeah. So yeah, this is Gauss's other theorem. So if we plug this in to our integral form of Gauss's law, we get the volume integral of del dot E dV equals Q enclosed over epsilon naught. And if you remember from the definition of our volume charge distribution, the total charge of something can be expressed as the integral over the volume of your volumetric charge distribution. And so something to note about integrals. If you have two integrals equal each other, this can, over the same volume, this can only be true, this can only have equality if and only if whatever's inside of the integrals is also equal. So we can end up dropping the integrals, and we get del dot E equals rho over epsilon naught. And this is the differential form of Gauss's law. This is usually the one people tend to recognize when you say Gauss's law, because it's just a bit simpler to write than an integral, I guess. Um, so yeah. So yeah. So how does this make our lives easier as opposed to doing that complicated integral at the beginning? Let's go back to our point charge. If we go back to our point charge and we actually look at the Gauss's law, you'll notice some things about this. So if you look at a constant radius, the E field doesn't actually ever change in magnitude over the surface at some constant radius. So and also, like I pointed out earlier, the electric field is everywhere parallel to the surface area vector. So I can drop the vectors actually. As long as I keep in mind that I know that this E field is pointing radially, because the surface vector of the surface I constructed points radially. And because the E field magnitude is constant over this surface, I can end up taking this out of the integral. And I get E times the surface integral of 1, which just ends up equaling the surface area of whatever surface you construct. So that ends up equaling not equals, E times 4 pi r squared, which is just the surface area of the arbitrary sphere we drew. And as per Gauss's law, this equals Q over epsilon naught. And so if I take this stuff over to the other side, I'm left with Q over 4 pi epsilon naught r squared r hat. And that is a much simpler way of calculating the E field because we didn't ever actually do any fancy calculus. We exploited the symmetry of the problem to avoid it. And so the point charge example is kind of a circular argument because I used the point charge field to kind of motivate Gauss's law. So let's look at a different geometry right now. let's look at a line charge. So a line charge, um, if you remember from last time, can be represented as with a line charge density that equals Q over the total length of your charge distribution. And so if I draw some random cylinder around this line of charge. So the reason I say arbitrary, right? Because Gauss's law holds for any closed surface. Whatever surface we draw, um, uh, is valid for Gauss's law as long as it's a closed surface, which means that we're free to pick any arbitrary type of surface that makes the problem easiest for us. And so what we call whatever surface we pick, um, we call it a Gaussian surface. Hence Gaussian surface. Yeah, there it is. Yep. I exist purely to make electrostatics problems easier. Um, so yeah. So if I look at the E field over this surface area, like just like with the point charge, if you'll notice, the E field around the line charge is always parallel with the surface area vector. So I can drop the vector part as long as I know that this is going to point radially, and I add it back at the end. And also, um, the E field is also the same in magnitude over the whole surface at constant radius. So just like with the point charge, we can take this out of the integral. And so the surface area of this part of the cylinder, um, because as you can see, no E field points up or down out of the top or bottom of the cylinder, so that contribution becomes zero. The surface area of the side part of the cylinder is 2 pi r times h. In this case, I'm going to call it the length because it corresponds to the length of your line charge. Um, so it's E times 2 pi r times L. And that equals the total charge over epsilon naught as per Gauss's law. So moving all that other stuff to the other side, we get Q over 2 pi epsilon naught L, or that's the line charge density, lambda over 2 pi epsilon naught, oh, I forgot the R, R hat. And if you remember, because we did this problem last time using the hard integral method, this is the same as we got last time. Except this time, we did it with no calculus. We didn't actually have to solve. If you remember from last time, there was ended up being some integral over 1 over like square root of z squared and yada yada. Yeah. We didn't have to do it this time because the charge distribution has symmetry. So we're free to pick whatever makes the problem easiest. And so, as a final example, let's consider an infinitely large sheet of charge. Now, obviously, an infinite sheet of charge is going to have infinite charge and, doesn't exist. But the reason why we consider it infinite sheets of charge for right now is because it allows us to not have to consider something called edge effects. The electric field, generally speaking, the electric field at edges of objects, charged objects, tend to be really complicated because that math, you don't have symmetry anymore, and so that the math turns into a bunch of complicated integrals. In fact, edge effects are so complicated, even up to my graduate level electrodynamics class, we still neglected them because most of the time you can't even solve those integrals analytically. You have to throw them into a numerical solver. So yeah. So if you have an infinite sheet of charge, just like this graph is depicting, the electric field is going to end up pointing either directly up above the away from the sheet or below it away from the sheet. And this whole time for the sake of simplicity, I've been assuming in every one of these diagrams that it's a positive charge distribution. Obviously, if it was negative, it'd be going into the sheet instead. But that's just a minus sign difference, so I'm gonna ignore it for right now. So yeah. So once again, I can draw. It's kind of hard to see because of the, you can't really manipulate a 2D image like that. If I draw another cylinder, a Gaussian cylinder, that goes through the sheet, then this time none of the E field ends up going through the sides of the cylinder. Instead, they're all going through either the top or bottom of it. So this time the surface integral, again, you can end up just pulling out the surface area element. This time, this surface area element is just the surface area of the top of the cylinder and the surface area of the bottom of the cylinder. So those are both the same. So that's just pi r squared. I don't know why I blanked on that. But 2 times that. So E times 2 pi r squared equals Q enclosed over epsilon naught. And I get E equals Q over 2 pi epsilon naught r squared. And the vector that points... Oh, yeah. Go ahead. What's your question? Pi or tau? Pi, obviously. Tau is boring. Tell me, what other Greek letter gives you an excuse to eat a delicious pastry on their day? What are you going to eat on Tau Day? It's like, I know you're boring. Pie is awesome, man. So yeah. So this vector that points talcum powder. I mean, okay, that is technically edible, but you're gonna eat was that baby like the diaper powder? Okay, you go right ahead, Astral. So yeah, the vector that points away from this plane, I'm just gonna call it n hat for normal vector because it's normal or perpendicular to the surface. So if you'll notice, if you have an infinite sheet of charge, obviously your total charge is going to be infinite. But that doesn't mean that it can't still have a finite surface area or surface charge density, because even if your Q is infinite, so is your area. So if you think of an infinite sheet, the area of an infinite sheet is going to be r times r, or r squared. So this just becomes sigma over 2 pi. Wait. Hang on. Sorry. You want the pi in here because our surface was was a arbitrary circle, so you want the pi in here. So instead, we can package our charge and our radius, because keep in mind this wasn't the radius away from the sheet this time. This radius is the radius of the top and bottom of the cap of the cylinder. So um, this just becomes sigma over 2 epsilon naught times n hat. And the reason why this is interesting is because, unlike our previous examples, this is not dependent on distance anymore. This E field stays the same no matter where you are in space around it. It's infinite. Because you have infinite charge, because you have infinite charge, the E field never has to decay as you move away from it. So this ends up being constant. Now, obviously, this is not realistic. You're never going to have infinite sheets of charge. But the reason why, if you've ever wondered why physicists still deal in these toy models or idealized situations that don't actually correspond with reality, is because they make good approximations for real life situations. So even though this doesn't hold true, we can't actually have an infinite sheet in reality. If you're close enough to a finite sheet, basically imagine you come up really close to a giant wall. The wall itself might have a finite extent, but if you're up close to it, you don't know that. It might look like it spans forever. So that tells us that if we're really close to a sheet of charge, the E field can be reasonably approximated as this constant value. And that makes measurements and estimations and predictions easier. So that's why we do these toy models. Is netherite in his bed? I don't know. I don't work with those kinds of materials. So yeah, that. So going back to our topic, our overall topic for today, divergence and curl of E fields. That covers the divergence part. The divergence of the E field gives you Gauss's law, and just to kind of package this all up, I explained what Gauss's law was. I just to put a neat bow on my name. A Gaussian surface any closed surface used to apply Gauss's law to some charge distribution, right? So technically, I don't exist because I can be anything, basically, as long as I am closed. So yeah. So now let's move on to the curl of the E field. So curl of E. So if you remember back when I did the vector calc crash course, I said that the curl of a vector field tells you roughly how much rotation the field lines tend to have. Basically, can't do the field lines point in a circular pattern roughly. So let's brute force this. So, okay. I'm going to do this in the integral form. So, um, yeah, actually, no, I'm going to, okay. So if I look at the curl of our point charge again, 4 pi epsilon naught r squared r hat. If I were to use the curl Where is it in this book? So I can make this easier by using the curl in spherical coordinates. If I can find it. I know it's here somewhere. There it is. So the curl in spherical coordinates is... Oh god, that's complicated. I don't want to write that out. Alright, hang on. Change of plans. I forgot how complicated that is in spherical coordinates. I'm going to do this backwards. Instead of looking at the curl, this still represents, like, this will make sense. Just give me a second. Hey, Comey. You missed it. You missed all the thing about my name. We moved on. I'm joking. How are you? Um, so I'm going to look at the curl of E by looking at the line integral of E. And trust me, this will make sense in a bit. So in spherical coordinates, I'm still going to look at the point charge. So some point A to B of, I'm going to wrap this in K. KQ over R squared. R hat dot. The line element in spherical coordinates is dr r hat plus rd theta theta hat plus r sine theta d phi phi hat. So yeah, if I take the dot product, these terms are zero because r dot theta hat and r hat dot phi hat both zero. So this becomes the integral of a to b of kq over r squared dr. These are constant, they can get taken out. And so the integral of 1 over r squared, kq ra to rb, 1 over r squared dr. So if Alepht's covered derivatives, an integral is basically an inverse derivative. So the integral of 1 over r squared ends up being minus 1 over r evaluated. So the straight bar just means evaluated from rb to ra. So that becomes kq 1 over ra minus 1 over rb. So that's the line integral, which tells me that if I do a closed line integral, so I start and end at the same point, that becomes 0. So I can say that the closed line integral around any path, because if you'll notice, I didn't even specify a specific path. It was just dependent on the initial and final position. This is 0. And so I can apply Stokes' theorem, which tells me that the closed path integral, so the closed equals so this is Stokes' theorem. If I use Stokes' theorem on the E field, this tells me that the surface integral of the curl of E, where the surface that I'm integrating over is the surface defined by this closed path as the boundary. But that's not important here for right now. So the surface integral over the curl of E is 0. And the only way for an integral, because again, we didn't even specify the path of the surface. The only way for this integral to be 0 always is if whatever's inside it is 0. So the curl of E is 0 for a point charge, which makes sense, right? Because if we go back to our graph of the line charge, there's no rotation in it, right? It all just points outward. It just tries to move away from the charge distribution. There's no rotation. So therefore the curl is 0. And so, and that is true in general for any electrostatic source. So, yeah, so I'll write it succinctly here. This implies that all electrostatic E fields, so any electric field generated by some non-moving charge distribution, so static as in, I misspelled that, I just realized that, my bad. So remember, electrostatic doesn't mean like static electricity, it means stationary. So any electric field generated by a stationary charge distribution are irrotational, meaning they do not curl. They do not curl at all. Because as per Gauss's law, as we found out, all electric field lines flow towards or away from the charge distribution. And yeah, that wraps up the divergence and curl of E fields, which includes Gauss's law and Gaussian surfaces.